Before I talk about the 4 theorems of the day, okay. Before I talk about the 4 theorems of the day, thank you. Let me ask you something before. Okay, so let's say I have a parallel line. Oops. Let's say that I have a parallel line like this. Another. Okay, imagine it's a line. Okay, now, if I have 2 parallel lines like this, what can you tell me about the distance between maybe point A, here's AB, and CD. And you guys remember the distance from a point to a line? How do we figure out the distance from a point to a line? It is the... No, there's a definition. How do we define the distance from a point to a line? Nicholas, thank you.
By the line that's perpendicular to the line.
Exactly. So if I want to... So let's say I have a line L and M. What is the distance between... I got rid of those points down there, but what is the distance between L to M? It is the perpendicular bisector. Thank you. Perpendicular segment from A to M. It's whatever that let me call this point C. Is that okay? Yeah. What is the distance from B to M? Again, the perpendicular segment from B to M. Let's call it D right here, and of course it's okay. So if this is, and then we know that L and M are parallel, okay? What if, right? If I told you this, can you tell me from here is 2? What is the distance from here to here? 2. Is that obvious?
Yeah. Yeah. I don't get why that's obvious.
What do you think it is then? If it's not 2, what do you think it should be?
What? 5.
Oh, you think it's 5? Why wouldn't it be 5? So who could explain? Yeah. The distance between right? Isn't the distance between these 2 lines the same?
Yeah.
Because we define the distance between the 2 lines from a point, right, to this line is going to be a perpendicular segment. So if this is 2, this has to be 2. Right? Is that okay? All right. Well, it's not writing. Okay. Give me a sec. Okay. Let me ask you another question then. Class, here. Let me ask you another question. If I have, again, instead of 2 parallel lines now, what if I have 3 parallel lines? Let's call it L, M, N. Okay? Let's say L is parallel to M, parallel to N. And let's say that I have, what is this called? Let's say the distance from here to here again is 2. Okay? From here is 2. Okay? Distance. And let me draw another transversal like this. By the way, what would this distance be? Would it be 2? I'm gonna say 2. Raise your hand. Okay. This would not be 2 because why not? Yeah, it doesn't have to be 2. Or if you wanted to make it 2, anybody know how to do that? Yeah.
Get the angles from the...
Yeah, if these 2 transversals will be parallel, then yeah. But they're not, right? So it doesn't have to. So let's say this is 3. Anybody want to guess? Austin, what do you think this will be?
3!
Yeah, why do you say 3?
Because it's the same transversal.
No, the distance between L and N is same as? Between M and N, right? Because we just showed, right, this is 2, 2. It's got to be 3 and 3. Would you agree? Yeah. So if this was, I don't know, if this is X, what would this be?
3.
Okay, so that's what this only works, listen, this only works if, right, this was 2 and 2, right? In other words, if these were same. Do you understand? Okay, let me ask you one more thing. How about if I had this triangle? Okay, and I have a point, that's a midpoint right here, okay? And if I were to draw here, let's say I draw a line that is parallel, let's say that's the midpoint. Let's say I draw a line that's parallel, that's through the base, but it passes through the midpoint of that side, okay?
Okay. Wait, what are you saying? What's that little scribble?
Yeah, I'm just saying these are parallel right here. This one and this. Okay. All right. Okay. Yeah, this is M, midpoint. Okay, because I have these 2 tick marks there. What can you tell me about this point N? Anybody want to guess what that point might be? So if I made this, so I have a point M, right? The midpoint of this side. It is a parallel to the base. What do you think the end will be? Anybody want to guess what this might be? Tony?
The midpoint of the.
Very right. Turns out if you do this, N will be the midpoint. It happens, yeah, always. You give me any triangle. Look, you give me any triangle. Let's do an obtuse.
Only for triangles, right?
Yeah, only for triangles. If you give me an obtuse, no, I just want to understand. So if here's an obtuse triangle. Here's the midpoint right here. So this segment is equal to this. I draw a segment, line that is parallel to the base, right? Through this point, midpoint, right? Okay, if I did that, guess what?
Oh, that's cool.
This is going to be always midpoint. It's always true.
Wait, it has to be obtuse triangle? No.
Or any triangle.
Any triangle? Wait.
Any question? I'm telling you, this is true. It's always true. Okay? One other thing. Let me draw another triangle. Again, this could be any triangle you want. Now, this time, I have a midpoint right here. And I have another midpoint. Okay? And I connect these two midpoints. Okay?
Oh my gosh.
Okay. If I did this, that segment, it's two things true for this one. One, anybody want to guess? It's sort of kind of, if you looked at the previous one, it's going to be, what can you say? Iveta? Very good. This will be parallel, right? So this will be parallel to that. There's a second thing. I don't know if you could actually, this one is sort of, it's not so obvious, but this is always true. Oddly enough, it's always true. Second one is, there's a second fact, this is always going to be true. Anybody want to? Oh, what do you think? You want to guess?
Since they won't intersect.
Oh yeah, we know that because they're parallel, yeah? Okay. So, yeah, of course, this one will never intersect with the base, this thing, because they're parallel. We just said that, they're parallel. But the second fact is sort of interesting. You may not realize. Jason, what do you think?
It's a
Bisector
bisector.
of what?
Of the sides.
No, we know these are midpoints. We know that this is midpoint.
Yeah, so it's a bisector, right?
Bisector of what?
The sides.
I know, but that's obvious because I told you that M is the midpoint of this side and N is midpoint of that side, okay? Yeah. Andrew, you've been very, can you tell me? We've been very patient here.
The angles are the same.
Which angles?
Oh.
Oh yeah, okay, so yeah, you're right. This angle will be congruent to this one, yeah, because these two are parallel, right? Hold on. Shh. Okay, John's been patient. Okay, what do you think? That's exactly, turns out if this is 2, this length right here is 4.
He checked in the book, he's a cheater.
Hey, guys, hold on. Guys. Okay, class. I know, come on. All right, so, guys, here we go. Yes, okay, good. Now, so if this is x, guess what this length is? Okay, let me get a little bit more trickier. What if this was y? What's the length of this going to be? Yeah, y over 2. It's always true. You give me any triangle, okay, guys? This is always true. So, I'm gonna say this is half of the other, okay? So, so you're like, why is that true, right? Guess what we're gonna do today? Yeah, prove these things. Okay, those are the 4 things we're gonna be talking about. Okay?
That's only 3.
No, we talked about 4 things, right? 1, 2, 3, 4. These are the 4 theorems we're gonna talk about. And you're right. You're wondering why does that work, right? So we're gonna help you understand. Is that okay? So if you're not quite sure why, okay, guys, listen. If you're not quite sure why, pay attention, okay? Because that's what we'll be doing. Is that okay? All right. So let's move on. Here we go. Today, so as you might have guessed, we're gonna be talking about theorems involving parallel lines. Okay, we have some other theorems, but we're going to actually include parallelogram. That's going to be sort of the key because we just talked about some properties of parallelograms last time, right? So let's see whether we understand. So write this down. Here's our first theorem. If 2 lines are parallel, then all points on one line are equidistant from the other line. Okay. So write that down. Oh, wait. And think about how this is very similar to the one that we just talked about, which is the very first picture that we drew. Here, let me move it up. I know, hold on, I'll get this. It's this one. Okay? So this theorem is talking about that. You should have it on your notes, right? Okay, so go ahead. Think about this. Does this make sense? Good question. You said, what's your question again? No, I just want you to say it again. No, I want to record this. Okay, go ahead. Yeah, because I want it to be into the recording. Go ahead. No, because it's a good question. What's your, say it again?
Isn't it like perpendicular?
Right, it looks like we're talking about these perpendicular segments, right? AC and BD, right? Because on the theorem that has nothing on the theorem that says these are perpendicular segments, right? So, why is that? That's a good question, because the theorem doesn't mention anything about perpendicular segments, does it? But why are we talking about now perpendicular segments like AC and BD? Yes, sir.
Because the definition of distance from a line to another, a point to a line.
Yeah, Young's correct. It's the definition from point to the line, right? Right? What do we know? What do they mean by that? When they say the distance from point to a line is what?
Same
Do you remember what we just said?
distance.
How do we define the distance from a point to a line?
Wait, there's like one
Hmm.
line? Wait, I don't get this.
Okay, go ahead and go back to your notes on 4.7, everybody. And look at what we said about the definition of a point to a line. The question is, can the distance from a point to a line be in any angle? The answer is
No.
no. Because we defined, somebody read it for us. Thank you, go ahead.
Okay. It's defined as it's the length of the perpendicular segment.
Thank you. So, Nicole, can you answer that question again? Would the distance from a point to a line be in any angle you want? No, then the distance could be any distance you like. Right? We defined this in previous sections, that the distance from a point to a line is a perpendicular segment from the point to the line. That's why you know that AC is perpendicular to M and BD is perpendicular to M. Yes, Amy?
All the time.
Yes, we defined this. This is the definition.
Do you have to say the definition?
I'm sorry?
Do you have to say the definition? Like
Yes.
write it down?
Yeah. We have a special definition when we're talking about the distance between a point to a line. We're talking about a line segment that is perpendicular from that point to the other line. Nothing else. Is this easy or hard? We defined this. This is a definition. I'm just telling you that's how we defined it. We did this in section 4.7. Right?
Yeah.
Okay, and so then what is this theorem saying? What does it mean? Nicole?
If two lines are parallel, then like if from the distance from a point to a line, like on all of them are the same.
Exactly. So you give me a point on line line L. The distance from that point to line M is always going to be same. If distance AC is 2, what's the distance from B and D? 2. If the distance of AC is X, what's the distance of BD?
X.
That's all he's saying. Yes.
What if it's like a transversal and it's not equal?
Let's go back. What do we talk about the distance from a point to a line, Austin? So can it be in any other angle?
So there's never going to be transversal.
Oh.
What are you talking about? Huh?
So we're talking about the distance from a point to a line, okay? And that segment has to be perpendicular. And so these perpendicular segments from these two parallel lines must be always same, the distance. No, what's your question?
No, right before she showed us.
Before I showed you this, Austin? This is the first picture I showed you.
It's frozen. It's frozen.
The second one.
I'm not talking about the second picture right now. I'm talking about this picture. That's why we're talking about the distance from a point to a line. Is this clear?
Yeah.
No. Who said no? What's your question? Okay. Any question? So then how are we going to show that this is true? How are we going to prove that if two lines are parallel, then all points on one line are equidistant from the other line? Thank you, Samantha.
So AC and BD are both perpendicular to them.
Right. AC and BD are both perpendicular, so
So then you know that they're parallel.
we know that they're parallel. How do we know this? What tells you that?
There's a theorem. It's like in a plane, if a line is cut by a transversal and they're both perpendicular.
Oh, yeah, that's the one. Who remembers that one? Yeah, Jason?
Oh, it's if two lines cut by a transversal and corresponding angles are congruent.
Oh, okay. You could use that too if you like. You could use the fact that the angle ACD is and BDB. Okay, this angle right here. Both of these angles are corresponding angles, right? Two lines cut by a transversal, right? You could use that. Two lines cut by a transversal, and the corresponding angles are congruent. Then these two lines are parallel. You could use that. Or the one that Samantha is talking about is what? If two lines are both perpendicular to one line, guess what? Those two lines are parallel. You guys remember that one? Okay, so that's true. So there are many ways of showing that AC is parallel to BD. Okay, good. And what else?
So then once you know that AC is parallel to BD, you also know that L is parallel to M, which is given, and then you know that ABDC is a parallel.
Exactly. Because AB is part of L and CD is part of M, what do we know about L and M? They're both parallel, Kevin. Not congruent.
Yeah, but after you prove that they're parallel.
You can't say that first though.
I know.
So therefore you're wrong. You need to say that AB is first parallel to CD, right, Kevin? Then we know that AC is parallel to BD. Then we have a parallelogram. Then afterwards you could say they're congruent.
Yeah.
Okay. So if that's what you meant, you're right. But you can't say that first. That's what I want to make. So therefore we know that AC is congruent to BD because you basically have a parallelogram. Does that make sense? So we know that then if two lines are parallel, then all points on one line are equidistant from the other line. Is that okay? Yeah, so you get ABDC becomes a parallelogram. That's basically why this is true. Yes?
I get the AC and BD are parallel. What does line L parallel? We're trying to prove that ABDC is a parallelogram.
Yes.
What does line L is parallel to line M have to do with anything?
Who could answer that question? Josh.
Because you know the parallelogram is two pairs of parallel lines. Then it's all the lines. If line L and M aren't parallel, then you can't make the parallel to both lines.
If L and M are not parallel, Yachan, would a line segment AB parallel to CD?
Oh no.
That's what you need that for. Because in a parallelogram, this is what Josh is saying. Both opposite sides of quadrilateral must be parallel. Okay? We have shown that AC is parallel to BD, but we also need to show that AB is parallel to CD. So by using the definition of parallelogram, right, we have a parallelogram. Any other question? Okay, let's move on to the second theorem then. This is now referring back to this picture that we had here. Okay. Remember I told you that if you have three parallel lines, right? And if this distance from here to here, this transversal is 2, guess what? You draw any transversal, these distances always going to be same. Correct?
Yeah.
So that's what this theorem is saying here. And again, let's think about why this is true. But this is what it's saying. If two parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. Okay. And so the picture that you should think of is this. This is what we just did. You guys remember that? Okay, that's what it is saying. Okay, write this down. And let's think about how you could prove this. Actually, this picture would help us to prove this. Okay, so think about that. So how would you go about proving this, guys? So first of all, what's given to us? We know that 3 lines are parallel. What do we know about AB and BC? They're congruent. So that's what's given. So actually, I have it right here. So we know that this segment right here is congruent to that. That's given to us. Okay. Now, in order to prove this, anybody see what we could do? John?
Prove that the triangles are congruent.
Yeah, if I could show that these two triangles, X, R, Y, is congruent to Y, S, Z, I'm done. Correct?
Yeah.
So I want you to take a moment and see how you could do this. But let me give you a hint. We're going to use these XR and YS as these auxiliary lines. And guess how we're going to draw these auxiliary lines? We want to, so that XR is, anybody? Not congruent. Parallel to AB, yeah, or AC. Okay, we want these parallel. And also, guess what? We're going to draw a YS, so that is parallel to BC, or same as AC, right? Does that make sense? So could we do that? Because point outside a line, there's exactly one line that is parallel. Does that make sense? So that's what we did. Now, knowing this, how can I show that two triangle XRY congruent to YSCs? Because if I could do that, then XY will be the XY and YZ will be the corresponding parts of congruent triangles. Does that make sense? Yes? Question?
Oh no, not a question. I like how.
Oh, you know how to do it? Okay, go ahead. Discuss with the group, and you could show them how to do it then. Go ahead. So let's go through this. Turns out, to prove that the two triangles are congruent, how many people were able to figure this out? 1, 2, 3? So a couple of you. Which ones did you use? Which property or postulate or theorem did you use that the two triangles are congruent? Kevin?
I proved that the 3 and 4 are congruent,
Mm-hmm.
and then 3 and 1 are congruent,
Good.
and 4 and 2 are congruent.
Good. Let's stop right there. Kevin says, don't we know that angle 3 and 4 are congruent?
Yes.
Okay. Why? Because two parallel lines cut by a transversal, right? So we know this angle is congruent to that. What else do we know, Kevin?
1 and 5.
1 and? Not 5. Okay, so first of all, we know that 3 and 4 are congruent. Also, because we drew that XR as parallel to AC, what do you know about then? These will be the two parallel lines cut by a transversal here. What do you know about angle 3 and 1?
Congruent.
So we know that 3 and 4 are congruent, right? And we know that angle 3 and angle 1 is congruent. What about angle 4 and 2? What do you know about angle 4? Angle 4 and 2 are right? These are congruent, correct? So would you not say that angle 4 is congruent to angle 2? Well, what can you tell me after this? So what? What can you tell me about angle 1 and 2? By transitive, everybody? They're congruent. So we know that angle 1 and 2 are congruent. Does that make sense? So that's great. So we know angle 2 and 2 are congruent. So what do we do next then? That's good. So because of transitive, we could say easily that angle 1 and 2 are congruent. Let me erase that. So. Okay. Anybody have any question? Yes, Jason? Angle 5 and 6 are also congruent. Because why? These are the corresponding angles. Good. Would you not agree? Because you have two parallel lines cut by a transversal. 5 and 6 are corresponding angles. We're almost done. We have two parts of these congruent, right? Okay. So then what can we say next? Actually, some of you were saying, why is this transitive? Can I write this over here? Angle 1 congruent to angle 3, right? So here, angle 1 is congruent to angle 4 by transitive. And then since that 4 is congruent to 2, angle 1 is congruent to angle 2. Is that okay? Do you see how they transitive? Okay. Now, we need one more thing. Then we'll be done. Anybody see what to do next? So we have two parts. Tony, what do you think we want to do?
Well, we could prove that AXRB and BYSC is a parallel.
Excellent. AXRB and BYSC are parallelograms, aren't they? Because why? These are parallel, right? These are parallel and opposite side. Isn't that how we drew these auxiliary lines? They're parallel. Therefore, it's a parallelogram. What do you guys know about the opposite sides of a parallelogram? They're congruent. So what do you know about AB and XR? Congruent. What do you know about BC and YS. But didn't we know that AB is congruent to BC? So by transitive again, what do you know about XR and YS? They're also congruent. Correct?
Yes.
Would you not agree? So for these angles we use transitive. For these sides we use transitive. Therefore, we know that these two triangles are congruent by angle, angle, side. Does that make sense? Question?
How do you know that AB is parallel to XR?
Because who could answer that question? How do we know that AB is parallel to XR? Yeah, Chan? Yeah, when we drew the auxiliary line, we make sure that AR is not just any segment through X. We wanted to draw XR so that what? XR is parallel to
Wait, I was just on the proof you have to draw a parallel
line XR because
that's parallel.
point outside the line there's exactly one line that is parallel. Do you remember that one? We talked about this before a long time ago. Point outside the line, right? There's exactly one line that is either parallel or perpendicular. You guys remember that?
Yeah.
So we use that to draw that auxiliary line. Does that make sense? Okay, so then now that we have angle, angle, side, we know that XY is congruent to YZ, which is what we wanted to show. Jason, question?
You know how AB is parallel to XR?
Yes.
So what's your reason? Like, what do we, if we state that, what do you write for the reason?
How do we draw XR, Jason?
That's parallel. So it's given?
When we drew the auxiliary line, we made sure XR is parallel to AB. So
Wait, so
that's because how you drew the auxiliary line. Through a point outside the line, there's exactly one line that's parallel, right? So that's why XR is parallel to AC. This is because of how we drew these auxiliary line. That's what we just talked about with her just now. Right? Question?
What is it? If it's already drawn, then do you have to say it to draw it?
No. But when you do this proof, it will not be drawn for you. Because what's given is, you're not given XR. Okay? Does that make sense? Any question? Okay, now let's move on to the other two theorems. Do you remember this picture? If I had a triangle, and that M happens to be the midpoint of one of the sides, and you draw a line that is parallel to the base, what did it do? It goes to the midpoint of the other side. Guess what? Our next theorem is exactly that, okay? Here we go. It says, a line that contains the midpoint of one side of a triangle is parallel to another side, passes through where? Midpoint of the third side. Okay. And again, we're going to draw this auxiliary line AD such that, anybody want to guess how we're going to draw this AD? Parallel to MN and BC, okay? And actually, to prove this, this is really, really, really simple. Let's see whether we could figure this out. As you write this down, think about how you would go about proving this. Okay, this one is really simple to prove, okay? Think about it. Anybody see how you could prove this, guys?
Yeah.
How? One person, two? Same two people again. 3, 4. Josh, how is this?
From the other obsidian theorem 5.9.
Yeah, the one right before this one. What? How many parallel lines do we have now? Now that we drew AD, 3 parallel lines. Here's a transversal. AM is congruent to MB. Guess what? The third transversal, AN is going to be congruent to NC. So you see how it comes really from the other one? Is that okay? And here's the last one. We don't have time to write, but I want you to understand what this is saying, and we'll go over this next time. Look, if you have AM congruent to MB, and you have a triangle, right? And AN congruent to MC, NC, right? We just said AM is what? First, parallel to BC, and also AM is what? Half as long as BC. Is that okay? And since we don't have time today, we'll go with this next time. But do you understand what he's saying?
Yes.
Does that make sense?
Yes.
Any questions?
No.
Okay, good.